All right. Hello, everyone. Welcome to Chemistry in the Kitchen as part of Homecoming 2020, the virtual homecoming. Um, and so this is not my real kitchen. All right. I'm so glad that all of you could join us. I'm Shubha Das from the Department of Chemistry, and welcome to Chemistry in the Kitchen. I do want to say right at the beginning, thank you to all you alumni, students, parents, whoever's joined in, faculty, and the staff, the whole CMU family who've sort of made this time possible. I know you're not here, and we're all trying to get through this, but I am so very grateful to all of you, and I hope that all of you will also take a moment to think about those of whom you care about, and also to reach out to others and make sure that we can get through this time. Um, I do want to take just a quick moment to thank a few people, Laurel Furlow and the others in the Homecoming Organizing Committee, Ryan and Jessica, whom I've interacted with, as well as Andrew in Media Tech, who's organizing this. This is, it's not a typical homecoming, and we'd love to have everyone here, and we do hope to have that in a little bit. But for now, thanks for tuning in, and thanks to these people for making this possible. I just also want to thank Nuno and Al Shuring from the MCS Media Tech, who've over summer given me tips on how to set up this thing. I'm in my basement, so it's not my dream kitchen, but the kitchen. It's just a dream. So and also thank you to Dr. Giselle Sherwood, who's in chemistry. And she's the one who's moderating this session. So the Q&A will be handled by her, and she'll relay the questions, because I might not be able to see some of the things on the screen. So with that, I will get started. As I mentioned, I'm in the Department of Chemistry. My lab is in the Mellon Institute, and we can't really go in there right now. But my lab works on at the interface of chemistry and biology. We make DNA and RNA for biochemical as well as biomaterial type applications with lots of wonderful collaborations. As I was doing that, some of the molecules that we make include things like lipids and fats, as well as sugars, and then there's flavor molecules. That's the one that circled is the A that's in DNA or RNA. But if you look at some of the other flavor molecules, those are very, very similar. The ones that are there in chocolate or coffee, and then we'll get to that in a moment. So because we work with all these molecules, I began to think that it might be a good idea to introduce this to students in a different way. And so a number of years ago, I don't want to say exactly how long, but it was before I had gray hair, I started a course called the Kitchen Chemistry Sessions. And this came in two flavors, one for non-majors and first-year students, and another one for chemistry majors and other who were a little bit more advanced in their knowledge of chemistry. So in the course, rather than go over the 5 food groups, we concentrate on the food molecule groups: water, fats, carbohydrates, proteins, and aroma molecules. The same biomolecules that we use in our research. And so today's small lecture and demonstration will be based on that, but mostly I'll try and talk to you about water, and I want to make this a very useful experience for you. So I will start with microwaves, especially because a microwave is very efficient at heating up water, and I will come up to that in a moment. I might speak a little bit about fats because I have a bunch of chocolate, and I hope you have some, or you will get some soon. So let's start with water. There are some concepts with water. It's a very simple molecule. I'm sure that most of you or all of you know that water, the molecular formula is H2O. There's 2 hydrogens and an oxygen. And there's a lot of concepts. It's a very simple molecule. There's a lot of concepts right here that are useful. Some are easy to understand, some are not so easy, and I'll try and go through that very quickly. So the bond between oxygen and hydrogen is a polar bond because oxygen is more electronegative, means it pulls the electrons closer to itself, to oxygen. As a result, the oxygen part of the molecule is more negative, and the hydrogen part is slightly more positive. And so that bond between oxygen and hydrogen is a polar bond, and the molecule is polar. There's another concept called hydrogen bonding, which we'll come to, and which is not that easy to understand, apparently. But I said I want to spend this time and make it useful for you. So I want to ask you if you know how a microwave oven works. And there'll be a few questions that come up in the poll just to see what the audience, their ideas of how a microwave works. So how does a microwave oven work? So the first question, could you please launch the poll? So the first question, how many of you have a microwave oven?
We launched the poll a while, and we have about an 84% agreement. 77 people have used it regularly, and about 15 have, but they occasionally use it.
Perfect. So then the next question.
Mm-hmm.
And in the meantime, I'm just going to get the microwave here so we can actually think about this and see how it's used. So, do you know how a microwave oven works?
Oh, answers are becoming quite interesting. Right now, we have a 8% population that says by magic.
Okay,
but
great.
We have
so hopefully
people who generally say, yeah, I know how it works very well. Some people have an idea. About 50% of the population says I have some idea. 20%, not really, but there's definitely the magic component within there.
Okay, perfect. So now that comes to my next question. Have you seen a microwave?
We're emphasizing here, not the microwave oven, just the microwave itself. There is a, what are you talking about? Answer, and a maybe. One person said, I heard that it's not good for a person to use the microwave for health, so I've stopped using it more because of that.
I'll address that question at the end. Please remind me.
Okay.
But coming back to this question, have you seen a microwave itself? Not the microwave oven. This is a microwave oven. Have you seen a microwave? And the answer, of course, is no. You probably haven't seen it because a microwave is a part of the electromagnetic spectrum, and it's not in the visible range, which you can see, right? Which is much narrower. So how do we observe microwaves? And this is something we do in lab and other things. When you do research, is you use something else to observe a different aspect. So if you want to observe a microwave, we can use a reporter, which gets me to my final question in the poll, which is,
have we ever put a light bulb in the microwave?
Have you put a light bulb in the microwave?
Hello, this is 2020. It's at least 4% of your population that says this is what we do. But in general,
well, I wasn't sure. Okay, so looks like most people have not done this. So I will do this for you, and I just want to say, if you're at home, don't do this, or at least if you do, don't do it on my. Don't blame me. Also, if you do it, make sure there's an adult. Make sure there's a responsible adult around. So let's try and do that. So here we have a microwave. Let me just zoom in so you can see this a little better. So here I have a microwave already inside. This is just another camera so you can see in. I have a light bulb. So what we're kind of trying to do here is to use this light bulb, because the job of a light bulb, and this is not the LED or the fluorescent, this is the old Edison type incandescent filament light bulb. Because the job of the filament is to glow when there's energy or electrons moving through, right? So the microwave is going to excite the filament, the electron inside, and they're going to move through. So we're just going to use this light bulb as a reporter so that we can observe the microwaves, right? So, and the reason we're doing that is to understand how a microwave oven works. Okay, great. So this is a light bulb. What I'm going to do is I'm going to put it towards the side. Can you see that it's on the side? Okay. Yeah. So it's not in the center. It's going to revolve. And I'm going to put it at full power. Now this is what is this? A 60-watt microwave, 60-watt bulb, sorry. And it's a 700-watt microwave. So you do the math. This is not, I'm not going to put it on for too long. And thankfully, you're, not right in front of this, so you should be safe. So I'm going to do this for about, let's say 15 seconds. So you can see this, right? Okay. So the question is, does it glow? Oh, there you go. And so that was glowing because the microwaves were incident on it, and you could see the filament glow. Was it glowing all the time? No. So that tells us something interesting, and that's actually why you have a turntable, so that it averages out and evens out. One other thing I want to ask you, and because this is important to using a microwave efficiently. So what happens when you put the microwave at lower power?
Most of our poll attendants, there are 40% that says they have really no idea. At 43%, they talk about the change in the frequency, so it has a lower energy. And 20% of our audience says doesn't change power, change time of the microwave.
Okay, so that's an important distinction. So that's something we can figure out, and then that's a hypothesis you can test, right? So what I'm going to do is I'm going to put it in the center where it should be focused most of the time, the light bulb, right? And then instead of full power, I'm going to put it at 50% power. So time cook, 12 seconds, and power level 5. Oops, sorry. Time cook, I'll do 15 seconds, and power at 50% power. So if it actually changes the frequency and the energy, then the light bulb shouldn't glow as bright, correct? And that's a hypothesis we can test. Does it change the frequency and the energy, and it's not putting out enough energy? Or it could be doing it at full power, but only 50% of the time. So let's check that out, and I'll explain which one of that and why. So here I'm putting it on. It's in the center. It's focused all the time, but nothing is happening. Nothing's happening. Nothing's happening.
Yeah, we're waiting to see. Nothing is happening right now. We do have a side question about the type of bulb you're using.
This is an incandescent bulb.
Right. So can you use a CFL bulb? A compact fluorescent?
No, so CFL bulb won't work for this, because that's, I'm just going to replace the bulb in case the first one is busted, which I suspect it might be. Oops, because I've used it a few times. All right, let's try this again. Time cook, 15 seconds, and power level 5.
Yeah, it's working now.
All right. So it's going on and off. Mm-hmm. But if you noticed, it is still as bright as when it was at full power. Correct? And the reason for that, and now I'm going to take this off and explain how this works. And the reason for that And the reason for that is the microwave is very efficient at heating up water molecules, right? And so you don't want it, um, or you don't um, want to turn it off to let the rest of the food cool, and then turn it back on again, so that so that it heats up again. So what a microwave does is a microwave works at 2450 megahertz, or 2.45 gigahertz, which means these microwaves are working, and you have a water molecule, and a water molecule can absorb, or it's the rotational frequency is very close to that 2450 megahertz. You can have other microwave frequencies, but that's the one the domestic microwaves work on. And so what happens is the water molecules will be rotated at these microwave frequencies, and then that energy which gets into the water molecules rather than the light bulb will then heat up. But water will heat up very, very efficiently, water molecules, right? And that's the energy, that heat, you want it to heat up other things, right? And so that's why you want to sometimes maybe pause or stop so that the other things can heat up, and I'll come to that in a moment. But let me just explain one other thing that you may or may not have, or likely may not have known. And that's to consider what happens when you have a lot of hydrogen bonding. So in the previous slide I showed you, these are water molecules in solution, so they're pretty far apart, or randomly oriented, and so they all heat up. But in a water, in a crystal structure of ice, the water molecules are all together, and you have what's known as hydrogen bonding, which means there's some kind of interaction, not like a bond between the oxygen and the hydrogen within one particular water molecule, but rather interaction between the hydrogen of one water molecule and the oxygen, which is more negatively charged, of a different water molecule. But in an ice crystal structure, they're all packed together. And as a result, when you put in microwaves, these are all held together by hydrogen bonds. And because there's so many hydrogen bonds, it's very difficult to break out of those interactions. And so ice will not heat up in a microwave, right? And I hope that this will be useful information for you in thinking about how to use a microwave. Because if you want to heat up ice, or things that are from the freezer, you want to put a little bit of liquid water on it, and then that will heat up, and then that will spread to the rest of it. Or you could, and that's why you use low power, because molecules that are non-polar, unlike water, those don't heat up very efficiently. So you need the polar molecules or water to heat up, and that heat to conduct through the other parts, right? And that's why you have the low power setting, so that rather than you putting it on, putting it off, and waiting for the heat to spread, that switches on and off for you, cycles on and off. It's still at high power. There are some microwaves which are a little bit more advanced, can change the frequency a little bit. But generally speaking, most microwaves, when you put it at a lower power setting, it heats up at full power and then cycles on and off, so that the rest of the molecules, non-polar and other parts, will heat up. And you can test this yourself, and I encourage you to do these experiments at home. You can make a small cup of ice, or put ice in a bowl separately, and then take the same volume of water in a, and you will see that the water will boil, but the ice will not heat up. Okay. Here's another sort of fun fact. If you take a molecule like carbon dioxide, so this is non-polar because it's linear, and so there's the minus and the plus, they sort of cancel out. It's unlike water, which will cycle and tumble around and rotate at microwave frequencies, the carbon dioxide molecule will not. And so the microwave, as far as I know, is the only way to make a warm, fizzy drink like Coke or any other soda. If you put it on the stovetop, you'll get bubbles from the bottom and nucleation, and most of the fizz will go away. But if you do it in the microwave, it will heat up and you will not lose most of the fizz. I mean, the solubility of carbon dioxide is lower at higher temperature, so you will lose some fizz, but not so much. And this is the only way I know to make a warm fizzy drink. I didn't say it tastes good. Uh, I just said this is the only way that I know that you can do that. All right. How does the microwave work? So it's essentially heat transfer. So it's the microwave oven is just a different way of providing energy and putting it into whatever's in the microwave, food or light bulb or whatever. So and essentially it's radiation. You do need some conduction, and this is what you need to be able to heat up nonpolar molecules. And so you need some time for this transfer. And that's why you go to the low power setting. Convection isn't really in operation, or maybe to some extent if there's a lot of water, and then you have convection in which the molecules are then moving around in certain ways to transfer the heat. So that's how the low power setting works, is that it cycles on and off, as you can see in the graph there. Okay, so I just want to leave this with you so that you know exactly how this works. If you put things near the oven walls, no heating happens there. So if you think about, if you tie a rope to the doorknob, for example, and you do that to make a wave, that's a node, right? And so the oven walls are nodes, so it's not going to have much heating. The maximum heating happens at the antinodes, where the wave goes up and down the most, and that's where the maximum heating happens. And so in the microwave oven, there's lots of nodes and antinodes, and this is dispersed. So you can actually map the microwave for hotspots, which is why you have a turntable to average out. And there's multiple ways you can do that. You can put lots of different water cups and see which ones heat up first. Or you can put marshmallows. I can see which ones heat up the most or melt the most. You can put chocolate. I don't really like to do it with chocolate because then that's a waste of chocolate. You can use cheese or cheese-like substances. That's better. If you're doing so, don't do it on a plate. Do it on a cardboard, because otherwise it's a mess trying to clean up cheese. Melted cheese on a plate.
Professor Dash, just a quick time
Yes.
check. We're at
Sure.
12:54.
Yes, you're almost done.
Right. So just let the audience know.
Thank you. And so there's also, you can put upper limits, and you can see all microwaves not equal, and sometimes you have too many nodes and sometimes you don't have too much. So that's why different microwaves operate differently. So it's always good to test it out. And remember, it's a 3-dimensional box. So with that, we'll get to the first recipe. And the first recipe is one that uses all of these ingredients. And you can quickly make this along. If you have a premix of all the solids, this is the cake flour and sugar and cocoa. It's very easy to make, and you can make this and you can use your knowledge. And I have the oil and the milk mixed here, and I'm just going to mix 1 egg, slightly less than 1 egg, and I will send you the explanations for this. So when you do this and mix it all together, it's a great recipe because you can put it all together, make a batter. And you can make this 10 times and then just weigh out what you need. There are some times in life when nothing but chocolate cake will do, and especially at those times you don't want to have a big giant chocolate cake in front of you.
Agreed.
Right? So for those times you can use this cake, and you can just make it either in a mason jar, or if you have a favorite coffee mug or something, you can just do it in that. And I have an example where you can sort of just do that. Well, actually, you want to make sure there's not too many lumps. So let me actually, you've seen this part, this part. I'll just show you. I don't have time to do it in the microwave, and I don't want to interfere. Don't forget to take the light bulb out of the microwave. I'm just going to go outside and just put it in the microwave here. And within 3 minutes, or so, you will have it. And all you have to do is take it out. And depending on your microwave, if it's a high power microwave, it'll be ready much faster. Um, I did it in my microwave in my real kitchen upstairs, which is a 1200-watt microwave. So here's the actual cake itself, um, which is just like the one in the picture. Uh, and I will now just tell you, and you can do this even in much smaller amounts. In fact, my daughter is an expert now in making this. So you can put a little bit of this batter in small uh, cookie paper cupcake things and make a cupcake, single serve cupcake. And that looks like that. And finally, I just want to very briefly tell you about fats, because chocolate is a very good fat, an interesting fat, and you can make lots of nice things with that. And here's, I will just tell you about the fats, because I think everybody knows that oil and water don't mix. So this is oil and water. As you can see, even if I do that, these will then separate out. Whereas if you take oil and water, and this, the only difference between this one and the previous one is there is a little bit of soap in it. So once you mix, it stays mixed. So unlike oil droplets in water, which separate out because you don't want to have a contact, and I mention this because almost everything in life you see will essentially fall into this. They're either hydrophobic, which means they don't want to mix with water, or they're hydrophilic and they want to mix with water, right? And so and these two will separate out. So if you know, most substances behave in one of those ways. They either dissolve in water or they dissolve in oil. If you do want to keep the oil and water mixed, as I said, you can use soap, because soap is an emulsion, but there's also lots of interesting foods that are emulsions, right? Like butter or margarine or mayonnaise. And the way to keep these droplets mixed and dissolved in that liquid is to use an emulsifier. Now, an emulsifier has one part which is water soluble and one part which is oil soluble, and that's why it can stick the fat soluble or the oil soluble or the hydrophobic part in the oil or air, and that's why soap can froth. And so that's how an emulsifier works. And what you need to do, you need to whisk it and break up the oil into small droplets, and then the emulsifier will coat it and will prevent it from all coming together. So one last thing I'll tell you about this is that please don't use too much soap or emulsifier, because if you use too much, then what happens is those soap molecules all come together and stick together by themselves and form these what are known as micelles, right? So you don't need to use too much, and which is why, in fact, liquid soaps are sold as dilute, because people use too much anyway. So let's talk about foams or emulsions and foams. These are a little bit more tasty than the detergent and soap as emulsifier. So I'm going to tell you about lecithin, and you can use soy lecithin as an emulsifier, and this is more tasty than soap. And so this last recipe works because it has lecithin, which is like a detergent molecule. It has a water soluble part and an oil soluble part. And in class, we've done this with all kinds of different things, but it's not possible for you to do this potentially with lecithin, depending on how available or not it is. But I'm going to share with you this last recipe, and you can make chocolate mousse in any flavor in less than 10 minutes. And the way to do this, and I've done this in hundreds of flavors over the years with the students, the one flavor, including, I think in the background in that first picture, you can see a bottle of hot sauce. That's the one flavor I would recommend you not use because then there's all vinegar. But chocolate and chilies, you can use chili powder. That's fine too. And it's very easy to make. Essentially, you can just take a chocolate bar. If you look closely at the chocolate bar, it has soy lecithin, a good chocolate bar will have cocoa, sugar, cocoa butter, soy lecithin, and it has soy lecithin because it needs to keep everything dissolved and homogeneous, so it's not grainy and crystalline sugar in it. And the reason this works Lecithin is the same. It has a water soluble part and a fat soluble part, and this is already in the chocolate bar. So you can use that fat by and make the chocolate mousse. So all you do is break up the chocolate, and I'll just show you how to do this. You can do this in less than 10 minutes. You can take the chocolate bar, break it up just like that, and put it into a bowl. And we'll see this in real time, and I'll speed it up. And you can make it in any flavor you want. This one is coffee. You can use all kinds of other, nutmeg or curry powder, or you can use other flavored liquids like pomegranate juice or root beer. Don't use something with too much sugar. Just make sure there are no lumps. Put it in the microwave for 1 minute. It's going to melt it, and then you want to make whisk it. You're just trying to make sort of like whipped cream. Remember, chocolate is a fat, and you've added the liquid, water or some other flavored aqueous liquid. And when you mix it together, you can do it. I've done it by hand in 10 minutes, and this is a fail-proof recipe. And we'll send this to you as well. You whip it till you get a foam. And at the end of this, you will see, and just make sure you don't lift the blades out while you're still spinning, because otherwise you'll get it all over yourself. And your walls will thank you for not pulling it out while you're whipping. And you will get a beautiful chocolate mousse at the end of it. That's how that looks like. And I did this just beforehand. And you get chocolate mousse in whatever flavor you want in less than 10 minutes. And so with that, I will stop, and I hope this has been useful. And I'm open to questions. If you can please type them in the box, and Giselle will help me address those. Thank you for watching. There are a whole bunch of other events at Homecoming. Thank you for coming to this one, and do go to the other ones. And I'm open to questions.
So we have a few. Let's go back to the one from the beginning. We had someone said, I've heard that it's not good for a person to use a microwave for health. So I've stopped using it more because of that. Can we address that?
Yeah, a couple of questions. So one of the reasons people think microwaves are not good is because the microwaves leak out. And that's not really true. I mean, those have been tested. What's inside is there's a Faraday cage, so the microwaves don't really come out. There might be some interference with your Wi-Fi, which also works at 2450 megahertz. 2450 megahertz is, some routers work at that. There's settings so you can change that. So, but in terms of health, microwave radiation to your body, that's not a danger. As far as irradiating the food, that's not really that different from heating up the damage to the food molecules when you heat up in a different way. Ultimately, this is just a different way of applying energy or to the food molecules. So when you bake something, for example, that's also radiation, infrared radiation, or if you heat up, you also energize those molecules. So you damage some of the molecules. So it's not that you damage the food or make the food bad or it's bad, and you create things that are bad for health in a microwave that much more differently. So in fact, the microwaves don't penetrate the food that much. It hits the surface of the food, and then that energy goes in towards the center of that, whatever chunk that is, right? And so there's, as far as I know, no special danger from microwaves compared to other methods. It's just a method of, putting energy into whatever it is inside the microwave oven.
Okay. Can we go back to that question on the CFL bulb? So you had indicated that we can't use the CFL bulb. Can you go a little bit more as to why we cannot?
Well, CFL bulbs work differently. Of course, you can put it in, but you won't get the same effect. So in a incandescent bulb like I used here, there's I can show you this. This one is slightly better. This one has a filament inside, which is metal, and it's a closed circuit loop. A CFL bulb essentially works because there's a gas inside and there's a coating inside the bulb, which then gets irradiated, and then it's fluorescent. That's why it's called a CFL. It's a compact fluorescent light. In this case, it's the filament inside, which is a metal filament, in which when the electrons go through it, the filament glows, because that excess energy from the electricity, that energy which goes in, is emitted as light. So it works differently. So you can put it in. These, at least you can see the light bulb glow, the filament glow in this one. The CFL bulb just works very differently.
Okay. How is it that you can put the metal? So the bulb itself has a bit of metal at the bottom. How can you put that in a microwave without causing a spark?
Yeah, so metal is okay, for example, to some extent. For example, I make popcorn in the microwave. I put it in a paper bag and I just put a staple, right? So the danger comes in if the metal is sharp. For example, there are some microwaves and you have a metal rack inside, and that's used. And there's some microwaves that are built which have also a heating element, so you can do other sort of heating, so you can sort of brown your surfaces. Those kind of grill microwave oven combinations exist. Those have metal racks. So you can put metal. The danger with metal is if there is something sharp, all the electrons flow there, and then you have a high concentration of electrons, and then you can get a spark, right? That's the danger. But for short amount of times, if, for example, you can put foil, for example, thin foil, as long as there are no sharp edges, you won't get that sparking, because the sharp edges are basically where the electrons then. So a metal, remember, is something that can conduct electrons very well, which is why metals are good conductors of electricity as well as heat. Things that are more dense are better conductors, right? Wood is not as good a conductor as metal. That's how it works. So because in conduction, the molecules that are next to each other just transfer the heat to the molecule which is next to it. So when things are dense, the molecules are closer together, and then you can transfer the heat. So in metal, if you have a sharp corner, the everything will conduct and then accumulate at that sharp point. So you have a high concentration, and then you get a spark. But otherwise, it's okay.
Okay. And on that note, let's talk a little bit about the experiment that you did with the bulb within the microwave. So there was a point where you said the bulb lighted with the same intensity. Can you explain that?
Oh, yes. So what I meant was, when you put it at full power, the light bulb will light up and you can see how bright it is. When you put it at low power, if the microwave works at a lower energy because you put it at low power, then you wouldn't expect the light bulb to light up as bright. However, what we observed is that the bulb does grow as bright as when it was at full power, except it doesn't go on all the time. So when you put a bulb in the microwave at low power, all that means is that it's at full power, but for 50% of the time, if it's at 50% power. That's what the power setting is on the microwave. It's a way for it to cycle on and off, so that there's time for the heat to spread to the rest of the whatever's inside.
There's a comment that says the Panasonic inverter technology attenuates the power rather than time, but most microwave ovens changes time.
Yes, so there are some technologies. So Panasonic inverter technology can actually change, but they don't have, you have 10 different power levels, but even the inverter technology doesn't have 10 different ones. They do have a slightly different power setting. So Panasonic has that. There are, I believe it was Sanyo many years ago, and I think you can get it only in Japan. They had a microwave oven in which you can actually, it has sensors to measure the temperature. So you can actually put a temperature setting, and that would actually be really useful, but it's probably more expensive to do that. But yeah, there are some slightly different technologies there. But the most common one is the one in which, there's a full power setting, and that's it. And then you can just cycle time using the power settings.
So rumor has it that if I put a grape in a microwave, I can create plasma. How true is that one?
Yes, there's all kinds of fun experiments you can do with the microwave, and encourage you to do it. Just make sure you do it safely. So yeah, so you can actually, if you put cut a grape and close enough. So again, remember in a microwave, when you have the nodes inside, the half the wavelength, and that wavelength is about 12.2 centimeters. So as long as things are within that close to each other, you could see some plasma, and grapes are used for that. So if you cut it and put them very close together, you'll see the spark jumping. So it's not always with metal necessarily. You can see that even from grape juice. So essentially, you just need an electrolyte, and the grape juice has some. And so when they're the two halves are kept next to each other, you can see that.
Okay, I'm going to turn to some more recipe-based type questions that we've had.
Sure.
Um,
Sure.
So this person says they've made the mug cake before, but it's a bit underdone, but it's still good. Do you have any mix-ins to add to this?
Oh, sure. So, depending on how you make it, and that's why. So the recipe I've sent out is kind of optimized. For that's why I said slightly less than one egg, because if you put in one egg, it becomes too eggy. But once you make it, so this is the one I just made, and as you can see, it's pretty nice, dense, and you can put in all kinds of things. That's why I like to put the chocolate mousse, for example. You can do that. You can put you can put a caramel sauce. Very easy to make caramel in the microwave. You just need butter, sugar, and cream. You can replace some of the butter with miso, for example, which will give you other flavors and umami. You can make a miso caramel sauce, but this might be slightly dense, and you can change or optimize your recipe based on your microwave. So if it's too dry, then you maybe heated it too long. The reason this microwave cake works is there's no leavening agent, and so it doesn't become too dry. There's no leavening agent because you don't need any, because in the microwave you're depending on the microwave heating up the water and steaming, and there's only one way for it to go, and it goes up, and that's why this cake rises and is leavened because of that.
So,
So you should be able to get all kinds of toppings and whipped cream or whatever to dress up your cake.
so I'm going to ask a question, sort of going off this leavening agent that you're
Sure.
asking, because there are recipes that call for baking soda because they feel the recipe tends to be a little bit dense, but they use like 1/8 of a teaspoon of baking soda in it.
Sure. If you use a tiny bit of baking soda, for example, this is the one I said my daughter likes to make, which is a small cupcake. And I'm just going to cut this open. Where's the knife here? I'll just cut this open. And this was made with a tiny bit of baking soda. There's no egg in this recipe. I'm not sure how visible this is, but if you look at the crumb, it's much better.
Yeah,
and some of that has to do with how well you've incorporated it, and how smooth your batter is, and if there are bubbles already, because then you'll have these air pockets inside, which is what you want. And so by having baking soda, that has some carbonation inside it already, and you'll have more air, slight, better sort of air pockets inside. There's also all kinds of other ways. You can use a seltzer, for example, instead of water, which has some carbonation, and so that would also help. So I can make other fancier ones using a soda dispenser, which will carbonate it. Then you don't need it. Ultimately, all it is you're making a foam, right? In the microwave.
So why does bread itself get chewy in the microwave, whereas in the oven it gets crunchy?
So remember, in the microwave, you're making it work by heating up water molecules, right? And so you are not going to get the browning and the crisping that are possible by other ways, which crisping depends on some amount of dehydration. So you can heat it more. All you'll do is make it very dry but you won't get that crispiness because you're still kind of trapping it within a very moist environment. Because when your microwave is closed, you do drive out the water by heat, but you still have that whole microwave chamber filled with the water vapor, so it's humid. So you're not going to get that crispness. You'll just dry it out by overheating and over steaming. Does
Sure.
that make sense?
Yeah, definitely. Just quick note that it's 1:17. We'll take about 3 or 4 more questions. We'll try to get all these questions together. It's optional at this point if people want to stay. We're happy to go ahead and answer questions, but we just wanted to give you a time check. Sort of back to a couple other questions. There's one about substitutions. So what would you use for substitution with something like lecithin if there's allergies to soy, or even like a sugar substitution?
So sugar, you can use other sugar substitutes. That's fine. So did you mean the soy lecithin for the chantilly? For
Yes.
the chocolate chantilly, you can't really use that because chocolate bars come with the lecithin inside. This is why this recipe is so nice, because all you have to do is take a chocolate bar and any flavoring agent and water. The reason soy lecithin is used is typically it's extremely rare for people to have soy allergy to soy protein. There's much higher rate of allergies or incidences of allergy to egg protein, egg lecithin, right? So you can get lecithin from eggs, which is why mayonnaise and so on works. You can make mayonnaise, which because you depend on the emulsifiers in the egg. But there's very few or much less known allergies to soy lecithin, which is also why it's much more widely used. But if you can't use lecithin, there are other agents, emulsifying agents to use, and some of them you can get. I don't know. There are specialty stores, but other food grade ingredients you can use.
Okay.
But these you can get sucrose esters, and these tend to be a little bit more esoteric. Sucrose esters in which they've attached lipid like fat like molecules to sucrose. And in fact, some of those are ingredients that you see in very highly processed foods, and those are there because they are good emulsifiers and have a way for you to emulsify foods and add things, but by adding very little bit of those ingredients.
Do you have any tips regarding like marinating foods, meats, etc.? For example, I've heard about using things like yogurts and acids to help break down proteins in the meat and make them a little bit more tender for cooking.
Well, so there's lots of things going on there, right? So if you want to tenderize meat, green papaya is used, or you can use there's I guess a lot of these meat tenderizers things that are sold. If you look at the ingredients, they'll say papain or something like that. Papain is an enzyme which is there in green papaya. You can also use pineapple, which has bromelain, and these are proteases which break down some of the meat and tenderizes. You have to be careful. If you let it go too long, then it becomes kind of mushy. That's one way, but the other aspect of this is flavor, right? Because you want to add salt and other things in yogurt. Those add flavor. Yogurt is also good because what you want to do is, again, if you're thinking about flavor molecules, there are all kinds of molecules. Again, they fall into sort of two categories, either water soluble or oil soluble, right? So if you have yogurt and oil or other things, those mix together, and then that leads to an overall better marination and all those flavor molecules mixing and getting absorbed. Does that make sense?
Sure. So will recipes be affected by altitude like it would in the oven?
Yes, to some extent, and actually to a large extent. So most things, most molecules, cells, all of that are based on water, right? And if you're depending on cooking it based on you heating it and the water getting heated up and all of that, then that's going to be affected by altitude, right? which is why also, pressure cookers are also useful, because then you're cooking it at a higher pressure, and so that's why it cooks faster. But if you're cooking or boiling something, and require it to boil for a certain amount of time, for it to get cooked through, but your water is going to boil at a lower temperature, then you have to take that into account in your timing, right? Because again, there's time and there's temperature, which is involved in cooking.
We're sort of at the end of the recipe-based questions, and we just have two more comments. Very earlier, someone was asking if the department is currently working on any projects with the computer science department to create like algorithms to do 3D printing of food.
I don't know if there's anything specific to in that regard, but I do know Adam Feinberg's lab was working on 3D printing, and he's doing some fantastic tissue engineering and so on with that. But they've also made a 3D printer, and if you have a 3D printer which you can use with ink or whatever, the printing material that is edible, then you can 3D print food. And I know 3D food printers exist, but from a practical purpose, those are essentially more for the novelty of it, as far as I know. But in the computer science department and so on, I don't know directly right now.
Okay. We have a comment about your T-shirt and a comment about your apron. Okay. It was fantastic, alongside the beakers and all the chemistry-related paraphernalia. And just generally, a big thank you for a great presentation. They were fascinated with it. I wish your course for non-chemistry majors was offered when I was a student at CMU, and a great praise and thank you.
Oh, thank you so very much. That's very kind. And frankly, that course has been so exciting because of all the students who've been able to take the course and who I've interacted with, and who've been so creative with all the things. Because in the course, what I do is I try to teach them the basics of science through food. But at the end of the course, the students come up with their own dishes for projects, but they also have, as part of the course, to explain the science behind that. And from chemistry majors as well as non-majors, what's been so rewarding is not just how creative they are, but how wonderfully they can explain the science behind that. So thank you for that comment. That means a lot. And I've really enjoyed interacting with all the students through this course. Thank you.
We have a person who says their 13-year-old wishes a science teacher is this cool.
Oh, thank you. That's very kind. I'm sure their science teacher is very cool as well. And if not, or it doesn't matter. You can do your own science at home or wherever it is. The same principles apply everywhere. So I would encourage them to go ahead and work on science, or think about the things that are all around them.
Okay, and now more of a technical based question, because your setup is amazing, where you have the camera and things that are zoomed in on different angles, and somebody really just wants to know how you're doing this.
Oh, well, I forgot to mention at the beginning, and that's really bad, to thank my family for indulging me with this setup here and doing this in my basement. I'm in my basement. So these are just my slides, and that's just off. See, that's just my computer, and this is plugged into my other computer, or not my other computer, my kid's computer, which I borrowed, and that's running a program called OBS, which I'm using to do Zoom. But otherwise, it's just a green screen with a laptop.
Okay, and you just
it took me a while to figure it out, and thanks to Nuno and Al Shuring of MCS, who helped me. And we have a good setup on campus for something like this.
Okay, so I'll send your email address so that you can offer a bit more insight into that as well.
Sure, absolutely.
For more details, if that would help. But that's the end of our questions. Thank you so much. It was fascinating, and I think everyone really enjoyed it.
Thank you everyone for tuning in, and hopefully we will have a homecoming next year on campus, and we'll be able to see all of you. Thank you all for tuning in.
Someone said Professor should check out CMU OLI Intro to Bio and Intro to Chem to accompany his courses. We actually do work on OLI in our Gen Chem courses, and we are definitely open to working more on setting up more of these OLI courses. So thank you.
Thank you.